So in the last class, we learnt about synchronous counters, wherein all the flip-flops were given the same clock. Now we have a different class of counters, which is known as asynchronous counters. As the name suggests, the clock will be different. Okay, for each of the it is not the same clock which we are going to use. So among the asynchronous counters, ripple counters are the one which are very widely used. So we will speak about ripple counters, and synchronous counters, which we did in the last class, it used the same clock. So here now we are going to study about ripple counters. Okay, ripple counters means the clock is not the same for all the counters. It is an asynchronous counter. So let's see how this works. For example, let's design a 3-bit ripple counter. So I have 0 0 0 1 2 3 4 5 6. It has to count like this, right? So here for the first leftmost, I am going to give an clock signal. Okay, now here I call it as count pulses, right, rather than clock, because no more it is not the same clock which is being given. So just the nomenclature, although it is a clock here for the first bit, I'll call it as count pulses. So with every count pulse, this is going to change from 0 to 1. So I can use a T flip-flop here. Okay, here now I have to decide what is the clock which I require to be given here, right? Till when we learnt about the synchronous counter, we were assuming that the clock is going to come here, and what is the T input which we require, which we have to give. Here it is, the design is differently. We are going to use T flip-flops, and both are already wired here. Now what should be the clock input? That is what we have to decide out here. Now if you see here, this is making a transition from 0 to 1, right, when this is toggling from 1 to 0, right. Similarly, this is making a transition from 1 to 0. Again, it is making a toggle when this is toggling from 1 to 0, right. Again, if you see 0 to 1 when this is making 1 to 0, again 1 to 0 when this is making 1 to 0. That means I can use a negative edge triggered flip-flop here and give the Q as a clock for this particular stage. Okay, so if you see here, now again for this stage also, if you see here, it is like it is all 0 out here. When this is making 1 to 0, this is changing from 0 to 1 here. Again it is 0 0. When it is making 1 to 0, right, it is making 0 to 0, it is not making any change. 0 to 1 also it is not making a change, and 1 to 1 is also it's not making any change. 1 to 0 it is again changing. That means I can use a simple T flip-flop here and T flip-flop here. Only I need to use a negative edge triggered flip-flops, and the clock is to be given from the previous Q. Okay, so that is how. So now if you see this implementation out here, and the same thing has been, this is an T flip-flop where I have given right, T is 1 for all the 4 of them. So all of the 4 are working as a T. Only thing is the clock is different out here. For the LSB, which is on the top, I am giving the count pulses or the clock. So with every count pulse, this will keep changing 0 to 1, 1 to 0. Whereas here I am taking the output and I am giving it here. So if it has to count, so if you see here, when this is making a negative transition 1 to 0, only then these have to be triggered. So that is the reason I have used negative edge triggered flip-flops. So you will find a bubble is there in all the 4 cases out here, right. And also I have a clear signal, that is to initialize these to 0 0 0. Whenever I put a clear signal is equal to 0, reset bar, all the you have a bubble out here. So that is why it is active low signal. So I give clear is equal to 0, this will get cleared, right. So that also we can do here. Now this is also in same circuit. The only difference out here is instead of T, we are using D flip-flop, and we know we have learnt already how to convert an D flip-flop into T. That is by giving the Q bar into D, right. So once you give Q bar into D, this will become a T flip-flop that we studied in the last class. So that is the only difference out here. Now since again here also it is a negative edge triggered, and like we said, it is important here. Like in the synchronous counter, we said, when we decided, if you remember, I told that it has to be, it can be either positive edge triggered or negative edge trigger. The count will change depending on the, if it's a positive edge trigger, during the positive edge trigger it will change, and if it is negative, on the negative edge trigger the output would change. Here things are different here. Here I can't use a positive edge triggered flip-flop for an up counter. For an up counter, I have to use a negative edge triggered flip-flops only, right? Okay, so you have to be careful with that now, because in your practical exam you might have to implement some counters like this. Okay, so if you have an binary ripple up counter, you will see here during negative edge of the clock, from 0 0 0 it is becoming 1. So whatever the waveform for this circuit is shown here. So it is just counting from 0, every negative edge it will increment by 1. Okay, so this is known as binary ripple up counter, right? Now suppose I want to count, I have to make a counter which is down counter. So if you see here 1 1, right, and then it has to count 1 0, right, and then it has to go to 0 1 and 1 1 here. Now what is the difference out here? If you see here, both we are going to use a toggle flip-flop. So Q is put here, and then a Q bar, so both is a T here, right? So the both are a T here. Now it has to count down. Now in this particular case, now how can it count down? If you see here, this is from 1 to 0, it is remaining constant out here. 0 to 1, it is making a change here, and 1 to 0, it's remaining same. And then again, obviously in the next state, this will go to from 0 to 1, and this is going from 0 to 1. So you will find here in the down counter, from the Q0, right, it is positive edge triggered, right? So the only change to implement an down counter, I will have a T flip-flop. Okay, T is implemented in this particular case using D flip-flop by giving a Q bar signal here. Now this is the LSB, this is the MSB. Okay, it is drawn like that. So I am taking Q here and giving as a clock to the next state. Okay, now I am using a positive edge triggered flip-flop, because I will find there is no bubble here. So both these flip-flops are positive edge triggered flip-flops, and since I am using positive edge triggered flip-flop, this will count down instead of counting up, right? So now earlier we saw we were using a negative edge triggered flip-flop, that was the reason it was counting up. And now if I use a positive edge triggered flip-flop, then it will count as in the down. It will be a down counter, right? So if you see here, it will start with 1 1, and then it will become 1 0. This is the MSP, right? Then this will become 1 0 0 1, and then 0 0. So this is down counting, right? So this is a down counter. So that is how you can implement an down counter. Right. So also you can have an BCD ripple counter, right? So same way. So this is a 0 1. This is what we require, right? It has to count 0 1 2 3 4 5 6 7. Now 9, and then it has to come back to 0 here. So this is the state diagram for a BCD ripple counter. Now earlier we gave the same clocks to all the flip-flops. Now we are not going to give the same clock. Now let's see what we need to give, right? Now if you see here, this is 0 to 1, 1 to 0, like 0 to 1, 1 to 0, 0 to 1, 1 to 0. So I can there is no problem out here. So I can give an right, I can use a T flip-flop and give the count pulses here. So there is no problem here. What about this? If you say here, this is making 1 to 0. So I am going to use a negative. For up count, we said for up counts we have to use negative edge triggered flip-flops. So this is also making an up count. So I am going to use a negative edge trigger here. So here it is making negative edge. So this is traveling from 0 to 1. Again it is making a negative edge here. So because I am going to give this as a clock to this state, right? So this has become the clock signal for here. So here it is making an and I am, second thing is 1, this is is the clock for this, and second I am using a negative edge flip-flop. So this negative edge, 1 to 0, this will make a transition. 1 to 0, this will make a transition. 1 to 0, this will make a transition. And 1 to 0, here I'll find there is no transition here, it is coming to 0 here. So when this particular transition, right, should be blocked some way. Okay, that should not reach A1. So what is so special about this particular transition? If you see here, for in this particular condition, because it is 0, 9 and then coming to 0 here, right? So you will find that, and if you look at the truth table, you will find here there is an 1 out here, right? There is a 1 out here. So I can use this particular one to mask this particular transition. Okay, so how do I do that? If you see here, here I am giving for the LSB, I am giving this particular directly count signals. I am taking this as a clock for here, right, and I'm giving it here, right, and instead of giving toggle out here, I am giving one, J here, I am giving it from the from here, right, A3 bar. So initially this will be 0 here, this will be 1 here, so this will act like a toggle switch, right? So for the initial these conditions, whenever this is changing from 1 to 0, because I have given this clock as clock here, so whenever A0 is making 1 to 0, this will keep changing the state. Okay, so that will keep changing the state. But when A3 becomes 1, okay, when A3 becomes 1, okay, in that case now this will become 0. Now I have an input given to the J as 0 and K is making K is 1 here. K is permanently 1 for all these flip-flops, right? And because I have given J is equal to 0 here and K is equal to 1 here, so 0 1, this will go to 0, right? And when will it go to 0? Whenever there is a clock transition, like when it is going from 1 to 0, A0, okay, that is the time it will sense that J is 0 out here, right? So it will this particular will go from so this will get continue to remain in 0. It will not make a transition out here, right? Because J is 0 in this particular, because I have given this bar out here. So that is how A1 is implemented. So sorry. So if you see here, A1, it is implemented by taking an Q bar from here and giving it to J. Okay, so that is how. Now let's take the second A2. So A2, if I am going to give this as a clock, so here, okay, 0 0 0 0, negative edge only, it has to change. 1 to 0, okay, it is changing the state, no problem. Again 0, this is a positive edge trigger, and so this doesn't make any difference because I have to look after only for the negative. So here it is making 1 to 0 here, 1 to 0 here. So that means there is a negative edge here. Is it making a transition here? It is making. So I don't have to do any additional circuitry for A2. I can straight away give the output of A1 as a clock to A2. So if I go to this circuit, so here I am giving it as a clock to this. Okay, now what about A3? Now if you see A3 here, okay, it is when is it making a transition? Here, 0 to 1 here. It is making a transition from 0 to 1 here. So okay, so that means I require if I use a T flip-flop, I require 1 to 0 transition. So that is available here also, here also, here also. So that is available here. Let me take up. Suppose I am using this as a clock, right? So if I am going to use this as a clock, right, it will make transitions at these places also, right? So I don't want that to happen. So what can I do? I want only during this transition, this has to make a transition, right? So if you see here, I am taking A2, I put an and an A1 and. Okay, what happens if I take and like that? So during this transition, right, they are not ones, so it will okay, that J is not now, so I am blocking that J is 0 in that case, so this will continue to remain 0, right? So because I have taken and J is being given and from here and from the previous state, so I have taken this as clock, but J I am giving it through AND of these two. Okay, so now it will not make a transition. Here it is making again 1 2 this is 1 2 0, here also 1 2 0, it will not make a transition because they are not ones. Here it is making 1 2 0 here, so there are two ones out here, so it will make a transition here, right? So it will make a transition from 0 to 1, right? So here it will not make any transition. What about here? Again 1 2 0 it is going here, right? It is going 1 2 0 here. So what will happen here? This is not both are not ones. Okay, so I will feed a 0 here into J, so automatically this will become a 0 here, so I don't have any additional. So if I just do an AND here with then A2 and A1 and give it as a J here, so this will this particular series will be generated. It will act like an BCD generator. Okay, so this is the circuit. So by mostly in asynchronous design, through visual inspection itself, we can simplify the circuits. Okay, so if I require a multi-digit BCD counter, like if I have to count 100, 101, and after 99 it has to go to 90. So each of them will be a BCD counter. And then the initial clock, like this clock, okay, will be A3 will be going here, right? And this will be this whole block which we have done. So this will go as an A3 will go as an input, okay, the stop input for the next counter. So this is how a multi-digit BCD counter also can be implemented. Okay, so thanks a lot. That's all for